Welcome everybody back to Paleo Talks. This is episode 50. We've made it this far and we are really excited to have Megan Emery-Wetherill with us today. How you doing, Megan?
I'm doing good. How are you?
Doing well. And I'm coming to you, we are coming to you from the Center of Excellence in Paleontology at East Tennessee State University in Johnson City, Tennessee. I'm coming to you from a hotel that has an ant infestation just north of Nashville. And trying to accommodate my son here at the same time. Just a second, Blair. And we are, again, just excited to have you and to be on episode 50. This is fantastic. I think at the end of the show today, we might talk a little bit about the future direction, how often we're going to continue this show. But let's move over to David for just a minute. And David's going to remind everybody how the show works.
Absolutely. So even though it is a big milestone episode for us, we're going to be sticking to the same usual format. We're going to start here in a bit with an introduction of our guest and then our guest's presentation. And when the presentation is done, the rest of the program is going to be Q&A. And so some of those cues are going to come from our panel, but the rest are going to come from the audience. So when that time comes, we're going to remind you to put your questions in the comments of the Facebook video and we'll read them for our guest to answer. And as always, if for any reason you can't leave a comment on Facebook, you can head over to the Gray Fossil Site's Twitter or Instagram account and send us a message there with your question. I'll be keeping an eye on that as well.
All right. Thank you, David. And thanks again for joining us, Chris, who's here again today. Been here almost every single time, and you can see he's in his museum office and he has a lot of books.
I am at the Center of Excellence for Paleontology today. Yeah. Although I do have a question. It's 50 episodes. How have we not talked about Oreodonts or Pokemon yet?
I know. All right. And I'm glad we're doing it at the same time because those are two important parts of our culture. Certainly with Oreodonts, how can you be a paleontologist without talking about Oreodonts? And it appears to me more and more that I need to learn about what in the heck Pokemon is. So this is fantastic. Again, great to have you, Megan. And the way that we start this show is for our guests to tell us about themselves and how you got into paleontology in the first place. What was that path that led you down this trail? And then tell us about where you're at right now. You're in Arizona and the position that you have. You're not in Arizona. You are in Arizona.
Well, we'll get to that in a second.
Okay. All right. Great. Maybe some updated news, I guess.
Yeah. Well, more like COVID lack of an update.
Okay.
So I got into paleontology when I went to a summer camp. Well, technically it wasn't a summer camp, it was an outdoor school, but apparently that's an Oregon thing, which is like summer camp, but where you go with your entire 5th grade or 6th grade class in the middle of school for a week. So we went out to the Clarno nut beds, essentially. So over in the John Day area of Oregon, and spent a week out there. And I immediately fell in love with paleontology. And then I left it for a while because, as I'm sure everyone knows, there's not exactly a lot of jobs in paleontology. So I worked as a wildlife biologist for a little while and then finally came back to grad school. I am not technically in Arizona, but I am an assistant professor at University of Arizona. This was my first year, but because of COVID, I haven't moved. So I am still stranded in Washington, living in a converted airplane hangar that has a serious wasp infestation. So
we have insect issues, don't we?
Yeah. I don't think any of those are going to fly by, but we'll see. I'm kind of used to it at this point. So if there's like a bug dive bombing me, don't worry, it's fine. I'm a professor at University of Arizona, but everything's been online, of course. So I've just been teaching online from Washington still. But
you were a grad student in Oregon.
Mm-hmm.
Is that correct? And what was your project there?
Oreodonts.
All right, very good.
Yeah, so my dissertation is on basically like the ground steps to fix Oreodonts. I think part of the reason that people know a lot about Oreodonts but don't necessarily do research on Oreodonts is because the second you try and write a paper, you realize that the taxonomy and your ability to identify an Oreodont is hard. Like
Right.
you essentially have to rewrite Oreodonts in order to write a single paper about Oreodonts, which is a big task. So part of what I did for my dissertation is I studied modern artiodactyls to figure out how variable they were. Because part of the problem with Oreodonts is they've been very badly oversplit. There are way too many species. And according to modern artiodactyls and how variable they can be, we don't need that many species of Oreodonts. They're probably just a lot of weird boys and girls all shoved together. And so, yeah, a lot of what I did with my dissertation is figure out how to shove them together. I did a little bit of shoving together, and then what we'll talk about today is a little bit more of that like consolidation process to figure out exactly how many Oreodonts there are. Still a lot. Yeah.
Fantastic. We're excited to start this. Let's share your screen.
All right. Again, which screen is it on? There we go. Too many screens. All right. So what I'm going to talk about today is we're going to talk a lot about Oreodont trunks and how weird they are and how many times they evolved and why. And so this is kind of a continuation of a project that I've been doing with Canada, Kyla Grande, and Paul Barrett and Ed Welsh, basically looking at phylogenetics of Oreodonts, you know, kind of because that's an important thing, but also to try and figure out, you know, how many times exactly did they evolve trunks? So if you're not, I'm sure you're all relatively familiar with Oreodonts. It's kind of hard to go anywhere near a mammalian fossil without also stumbling into an Oreodont. So you might be familiar with the basic model, Myricoidodon, Miniacharis, these sorts of white river things. They're usually like kind of this color with this like rosy patina. They're not actually the earliest Oreodonts. They're just definitively the most common. And I am really sad that my, well, I guess I can't actually, I may have called them a curse word in a paper and my reviewers are making me take it out. So I called them the basic, you know what, of Oreodonts. And that really is what they are. They're the basic model is what we'll say on the internet. But they're just really, really common, but that doesn't actually mean that other species of Oreodonts are common or that all Oreodonts look like this. So some of the cooler variants of Oreodonts, things like this. So we got stuff like Agriochirus on the upper hand. Agriochirus had claws, not hooves, and it was probably climbing trees. We have Leptokinia down in the lower left-hand corner. I'm not super convinced by the argument that they were swimmers, but they do have faces that look a lot like beavers, and it's an exciting twist. So I just like to promote it, even if I don't think it actually is the truth. It makes Oreodonts seem cooler, and you still have to go through and reject it. So there you go. Swimmers until proven otherwise. And then, of course, we have the jerks, which would be the Oreodonts that were traveling in herds. You might be able to tell that there's like some really rough texture on their cheekbone. That is because Primaricochirus, they have basically massive bone infections on their face, probably because they were biting each other and giving each other actinomycosis. Beautiful. And then the ones that we're going to focus on today are the Oreodonts with trunks. So this is Myricochirus. It's actually very closely related to the one on the top, but it basically lost part of its, it looks kind of Voldemort-y, right?
So
its nose has returned.
Were they jerks because they were biting each other?
Yeah, they were just really, really mean to each other. I need to finish that study, but about 60% of that genus of Oreodonts either has bite marks that are healed over, it has broken zygomatic arches. There's some that have zygomatic arches that have pulled apart and show some signs of trying to heal back together before the animal died. They have massive bone infections that were they were like zombie Oreodonts. They must have just been walking around with like faces full of bite marks and pus.
That is so cool. I've never heard of anything like this. Has this been published before?
No, I need to. So part of the reason it hasn't been published is because I need to figure out how many species of Primaricochirus there are before I can publish. So yeah, there's like a cascading series of papers that have to come out before that one. But I have talked about it a couple times at SVP because I can't control myself because it's so cool and I want to publish it so bad because it's so weird. And also, man, I want to get somebody to do some paleo art for that because that sounds pretty epic. And gross. So yeah, trunks. Yeah, so they're often called proboscis. I don't like that term. I think that it's way too technical. There is also an entire paper written on how we should be calling different types of trunks, different types of proboscis, and I think that's a little silly. So I'm going to stick with the term trunk. And of course, you all know elephants, and there's a lot of other animals that also have trunks. So things like tapirs, elephant seals, saiga antelope, dik-dik antelope, elephant shrews, just to name a few. Part of the reason that I study trunks is just really because they're ridiculous looking. So if you've ever looked at pictures of tapirs, and I have scoured the internet for the worst photos of tapirs that I can find, they're just kind of ridiculous. And tapirs, I think, are kind of a good introduction, because elephants, while we all know that elephants have trunks, those trunks are kind of an extreme end member, whereas a tapir has a much more refined trunk, which they use for selective foraging, and weirdly enough, for sniffing in different directions, because somehow they are just too lazy to move their entire body. So they have like this directional sniffing thing that they can do, which is what they're all doing in these photos, even though what it looks like is they're just making stupid faces. And of course, the babies are really, really cute. But dik-dik and saiga antelope are also a really important parallel, as we'll kind of talk about. But just in case you haven't seen a lot of dik-dik antelope, that's what they look like. They have much, much smaller trunks than tapirs or even saiga do. Saiga look like something that stepped out of Star Wars, but they are a real animal, and the males actually have much bigger trunks than the females do. And so with fossil animals that have trunks, it really is kind of all about the bones. There are some really, really consistent features that you can see, even just like without a paleontology background. It's pretty clear looking at these three animals, which ones would have the trunks, right? So if you're not super familiar with mammalian anatomy, here's where the eyeball goes. Here's where the nose goes on the elk. And then here is where the nose goes on the tapir. That's where the nose hole is on the elephant. And you can see that the orientation of nose to eye is very different. And this is really consistent in all animals that have a trunk. They have this shrunken back kind of pug-like face, because they're basically making all of this space and this room for trunks. Now, for a more technical overview, there are a couple of papers that have come up with this list of 12 characteristics that have occurred in most things that have trunks. I'm going to really quick, I forgot to change this so that it doesn't just, I want it to automatically do it. But essentially, it's like itty bitty nose bones, you kind of have like pug eyes, you have a really big hole for your facial nerves, you have lots of room inside your skull for sniffing, and you have a really big fat neck to help support all of the big fat face stuff that you just put on your skull. And basically, really what this all is it's moving all that bone up. Because when you're putting a trunk on an organism, if you just tried to plop down like a big fleshy trunk on their face, they would not be able to see around their trunk. And seeing is kind of a criteria for most of these animals to live. So they have to move something out of the way so that they can have space for all of that big musculature. So they basically move the bone so that they have room for all of the muscle. So this is a skull, this is Brachycrest, so this is an Oreodont, and Brachycrest has been known to have it for probably over 100 years, because when you look at it, it looks like a tapir skull that someone kind of stepped on. They look kind of like a misshapen boot. So up here is, can you guys see my little pointer? Okay, yeah. So up here is the nasal bone. It's very, very small. And you can see that it is basically retracted and made that nice pug face that we kind of recognize as being something that has a trunk. But the thing about Oreodonts is that it's actually not just Brachycrest that has a trunk. We have, I'm going to use these colors kind of consistently. So we have Brachycrest in yellow, Ustatocharis in green, and Merricocharis in blue. And so these are kind of the three genera that have signs of trunk development. But as you can see, even just looking at these skulls, they don't quite look the same, right? Like Brachycrest is kind of an extreme end member, but Ustatocharis and Merricocharis are much more modest. So kind of my question going into this project was, so did you just get trunks once in Oreodonts and then it just got really extreme in Brachycrest? Or do you have some sort of re-evolution of trunks? Right. So do you have it so that you have some sort of convergence over here on the left, or do you have some sort of ancestral characteristic state like you do on the right? Did you all go trunk all at once, or did you go trunks periodically because trunks are super cool? And so this is kind of the topic of the paper that I have in revision at PeerJ with my co-authors, basically trying to use phylogenetics to figure out essentially just, we're trying to solve the genus level taxonomy of Oreodonts using phylogenetics. How do they all cluster together? But as a side effect, we also kind of figured out the answer to this question. Not only how do they all fit together, but how do trunks evolve in Oreodonts? So this is kind of what we've got. And because our tree has like 150 specimens, so it's way too big to show on here. So this is a very reduced version. So with the phylogenetic history of Oreodonts, what we're finding is you have kind of those clawed tree climbing Oreodonts down here. Then you've got the itty bitties and the maybe swimmies. So your Leptokinia, your Bathogenes. Bathogenes, by the way, if you guys want to study an Oreodont, has crocodile bite marks in their skulls. Almost all of them. Very cool. Oreodonts are cool. That's the full scope of this talk. Oreodonts are great and you should study them too. And then you have Mericurus, Statochirus, and Brachycrus. But in between, you have things that don't have trunks. With Statochirus and Brachycrus, they also have a sister taxa that does not have a trunk. So it's looking like Oreodonts evolved trunks at least 2 times, possibly 3 times. The trees are a little bit unstable, so I'm pretty sure it's 3 times, but until we have like a more complete set of Oreodonts, we'll go with 2 to 3.
Megan,
so they're kind of evolving. Sorry, what?
Can you tell us again who it is that's having these bite marks from crocodilians?
Bathogenes, so the itty bitties and maybe swimmies. They have skulls that are like maybe this big. They're really, really small, and they're very cute. And there's a bunch of them down in Austin at the Texas Memorial Museum. They also have really cool endocasts. So, you know, they either have crocodile bite marks or they have brains. It's great.
Wow. And these are in aquatic deposits, I guess.
I don't know, actually. I just know that I was just doing, I was just basically trying to do phylogenetics at that point. So it was a lot of, oh, wow, that's so cool. And then moving on. So I'm not actually sure what deposits they're in. Probably though. No. Yeah, bite marks are kind of a common theme through Oreodonts. Sometimes they're doing it to themselves. Sometimes it's other animals doing it to them. They were a very large part of the ecosystem and they're very bitey. So trunks just in general are pretty common. So it's not really that surprising that Oreodonts evolved trunks 2 to 3 times because frankly, there's a lot of other organisms that have evolved trunks. You have trunks in marsupials, you have trunks in weird South American nodoungulates, you have trunks in all sorts of different things because trunks are super, super simple to evolve. So there's a master's thesis by Clifford from like 2003, where he basically talks about the fact that part of the reason that these things are so easy to evolve is mammalian musculature is facing that direction. So you basically have this big set of muscles that are already in the correct orientation. It's a very simple evolutionary step to make a slightly bigger lip so that you have basically selective foraging capacity. And then from there, it's really not that big of a step to take the trunk dive, right? So you start developing more lip structure until all of a sudden you have a trunk. So you would take something like an Oreodont and basically give it nice kissable lips, and then it just keeps going until they get sort of like Instagram lips, right? Just bigger and bigger and bigger. So the thing about Oreodonts is because we have enough Oreodonts, we can kind of test this particular hypothesis. Do you actually have this kind of change in lip structure that is leading, therefore, to trunks, essentially? And so you can look essentially at their most recent ancestor. So with Brachycrus and Statochirus, their most recent ancestor looked something like Phenacocylus here. They don't share the same common ancestor, but it's kind of the same general looking organism where you have a little bit of nasal retraction. This is actually not a very good example of nasal retraction, but you basically have a tiny bit of that like nasal notch starting to creep backwards, maybe showing that there's a little bit of lip development, but really not that much. This one has a particularly long nose for some reason. And then the weird thing is with Merrickicurus, its closest relative is Promericicurus, which doesn't really have that sort of structure. It doesn't have a short pug face. It has a very long face. And in fact, a lot of people think it might have basically a pig snout. So Oreodonts are demonstrating that potentially you can actually get trunks from something like this, where you might have like a cartilaginous pad at the end of your face that just happens to get slightly longer and develops into a trunk. I do want to do some like microskeletal structures to see if you can kind of tell whether or not there are basically scarring on the bone that are showing changes in that muscle direction or signs of a cartilaginous pad. But it's at least good enough evidence to suggest that trunks are maybe evolving in two different ways in Oreodonts, one through big kissable lips and one maybe through kind of a weird extendo nose from a pig-like face. So why? Oh yeah, trunks, they're super easy to evolve. Why? Why would you do that? They look so dumb. So even though they have a lot of convergence in morphology, they actually have a lot of different functions. Trunks are very useful for very different reasons. So tapirs and elephants, they kind of use them similarly. So same with the elephant shrew. They use them for selective foraging, right? They're a muscular appendage. They can move them all around. They can pick things up to certain extents. Obviously, the elephant is much better at this than like the tapir is. But that is not the case for something like a saiga. A saiga can barely move its nose at all. I highly recommend Googling saiga or looking for the YouTube video of this baby saiga. It's just like 3 minutes of it vaguely twitching its nose because that's kind of all they can do. And it's very cute, but it's not a muscular appendage. But you'll see that there's a really big kind of lump right here. So saiga, the theory is that they actually use it as an air filtration system for dust. They have this massive vestibule inside their nasal chambers. So air with dust comes in, the dust settles out in the middle of that, and then they don't choke on things like ash. With dictyx actually use theirs for thermoregulation. They have a countercurrent heat exchange system in their nose. They can also use it for selective smelling as well. They have a little bit more muscular control than the saiga does, but they're not using it to pick things up or necessarily for selective foraging. They're just using it to keep cool in hot African climates. And then of course the elephant seal, I think it should be obvious. It's for being sexy. It is a sexual selection thing. The males have much, much bigger trunks. They do use it to amplify sound. So it is kind of like a little trumpet. And actually saiga do as well. So male saiga have much bigger trunks and they use them to make very, very loud calls for the female saiga to come and find them. So a lot of different potential uses for trunks. If we go back and we look at Oreodonts, why would they have a trunk? It's pretty obvious looking at Brachycrus that Brachycrus is like a tapir. So probably Brachycrus was using it the same way that a tapir uses it. But Statochirus and Merrickicurus look almost nothing like a tapir skull. They're very strange. They have similar characteristics, but it is not the same. So how can you tell what they were potentially using it for? So these studies were great, but they really focused on tapirs and elephants. They did not focus on saiga or dictyx. They didn't focus on animals that didn't have the ability to kind of move items with their trunk. So if you include dictyx skulls and saiga skulls, I can't find a better saiga skull. So the saiga skull has a lot of flesh on it still. You really actually don't have most of these characteristics. So these 12 characteristics hold up really well if you have a muscular trunk. If you don't, these two characteristics are functionally the only characteristics that you have in common. You have a retraction of the nasal bone, and you have the nasal bones tend to stick out a little bit. But even in the dictyx and saiga, they do not stick out nearly as much from the front of the face as you see in a tapir. And weirdly enough, these two characteristics are actually found in animals that don't have trunks. So if you look at moose and rhinos and camels, these are all animals that don't have trunks, but they have pretty big and well-developed lips that they use for selective foraging. So as a result, The moose has little itty bitty nose bones, but it doesn't really have the nose bones that's sticking out. The rhino has a nose bone that is sticking all the way out, but it doesn't really have, they're not tiny because they're holding a horn. And then camels have really tiny nose bones that are pulled back pretty far, but they don't have anything sticking out from the top. So not so like a diving board, right? That's what you see on a tapir. You have that diving board for mussels. But they also do have pretty well-developed muscles for holding up their giant heads. So there's kind of like this weird thing that happens with animals that have this, what I call a proto-trunk, where you have some of the characteristics, but not necessarily all of them. So really quickly, I'm going to show you where these features are because this becomes really important with Oreodonts. So the nasal notch is basically how far back it pulls. So it's where the nasal bones meet the rest of the face. Your nasal tips, that's the very tip of your nasal bones. And then your premaxilla fusion point is the point at which your premaxilla is fusing in the most posterior direction. So a lot of these organisms have big muscle scars across their premaxilla. So having a really thick premaxilla gives them a place to root some of their muscles. So if we cross compare Oreodonts and different animals with trunks, you don't need to necessarily look at the numbers. I've tried to color code this so it's a little bit easier to see. But essentially, Brachycrus is the same as a tapir in pretty much every characteristic. Statoceras and Mericurus are not. They have some characteristics in common with them, but they also have some characteristics that are in common with things like Saiga and Dictic. In particular, they have, Mericurus has what I'm calling the maxillary strut, which is this chunk of bone that just is still sitting there. It's not necessarily that I think it's actually doing anything. I think they just haven't gotten rid of it because they're not using a lot of muscular attachments. So it's kind of just still, it's like the appendix of nasal retraction. Oreodonts also have some weird characteristics of their own. Oreodonts all have the posterior extension of the palate that I'll show you in a second, where basically like the part that protects their nasal turbinate bones has extended back really far. Mericurus has a massive incisive foramina, which is the foramen that leads to the Jacobson's organ for smelling. And then Brachycrus has like a vertical nasal bone, like even more steep than a tapir. Looks like a mountain. So here is a really beautiful view of Brachycrus. And one of the things that you'll notice is you can see that this is the premaxilla, and it's actually got additional ridges on here so that muscles could attach. So there were muscles attaching to the trunk from the bottom. All of the teeth have actually fallen out here. All of the incisors have fallen out, but they're way smaller, which suggests to me that it's not really using its incisors to clip anymore, probably because it's got a trunk and it's using its trunk to selectively forage for it. Here is Statoceras. You can see that it does have some nasal retraction with a very beautifully cleaned specimen. You can even see some fluff that is still on there from a cotton ball. And it's kind of just like this weird little midway thing. So maybe it had a trunk, but it definitely did not have very much of one. And it doesn't really have a huge amount of muscular scarring down here either. So probably couldn't do a lot of moving of its trunk. Maybe it could wiggle it a little bit. So I suspect with the Statoceras, you have something more along the lines of like sound production, where you do have something on the face, but it's not something that is doing a lot of mobility work. And they don't have a really big incisive foramen, so it doesn't seem to have been maybe involved a lot in smelling. And then you have Mericurus. These skulls just look demented. They look so squished, but they're not. That's just the animal. So it has like this massive structure up here that does have some muscular scarring on it. So I do think it probably was able to move its trunk a little bit, but if you flip it over, that's the incisive foramen. It's this huge circular structure. So I suspect that they probably had some sort of enhanced sensory capacity that they were using this trunk for. So maybe some sort of like directional sniffing sort of thing. And then the thing that is the weirdest for me for Oreodonts is here is that posterior extension of the palate. So instead of having the palate end at the teeth, in trunked Oreodonts, but not in other Oreodonts, the palate actually extends posteriorly. So I wonder if they have a posterior extension of the palate, potentially to help cover up the nasal turbinates. So when you create a trunk, By reducing all of those facial bones, you actually reduce your nasal turbinate area, which limits your ability to do things like thermoregulate, and it can limit some of your ability to take out particles using those nasal turbinate structures, because those nasal turbinates help you do things like remove bacteria from the air that you're breathing and stuff. So by posteriorly projecting their palate, they might have actually been moving their nasal turbinates back, which I'm sure if I could actually like CT scan a very nice Oreodont, maybe I could actually see the nasal terminates themselves. But until that happens, I'm using this as kind of a proxy. And this might actually be for a very good reason. So Saiga antelope, if you don't know, 2/3 of their population died over the course of 3 weeks in 2015 because they got essentially this respiratory infection that then spread to the rest of their body. And what's really weird about it is that bacteria just exists in all animals at all times. It's just a really common piece of your microflora in your nasal cavity. However, with Saiga, it got out of control. It did not impact any other animal in that area. So other antelope, deer, dogs, nothing else was affected by it. It was just the Saigas. And this seems to be something that happens to them over and over again. This is a Britney Spears reference. I spent a lot of time very carefully photoshopping her hair back onto this Saiga. But yeah, Saiga do seem to, oops, I died from respiratory infection again quite a bit. And I wonder if that is part of the reason why having that posterior projection of your nasal turbinate section is something that was maybe beneficial for Oreodonts. I also strongly suspect that trunks are a terminal adaptation. I have not been able to look at it fine enough at this point in Oreodonts to be confident, but it doesn't seem like in Oreodonts, basically once you go trunk, you don't untrunk. There is no backwards progression of that. It seems to be a bit of an adaptive valley. And if it does things like increase the potential for wiping out 2/3 of your population from a respiratory infection, it might be something that is maybe not the best thing to not be able to go back from. Because
tapirs, when we look at tapirs, there's certainly a long-lived, a stasis in this form.
Yeah.
For
Same
such a long period of time. So they were doing it. Yeah.
Elephants did it and they didn't go back either. And maybe it's just because trunks are super useful, but also it seems to be very easy to evolve a trunk. I'm not confident that it's very easy to unevolve a trunk. Seems a lot more like guided, which of course is not how evolution.
This picture.
She's so beautiful, so charming.
I'm really curious about Brachypelma now that you've enlightened me on that group, and it looks like it could be a scavenger. Just looking at how the robustness of those masseter muscles and the zygomatic arches, they're so huge.
Okay, so let's go back to that really fast because they're even weirder than you think.
Okay.
Because you can't quite see it. This ridge here is real. So they actually take the meeting of the, oh my God, why am I not, the parietals and the temporals. It's cool. It's not like I study skulls or anything. And it becomes like an inch tall ridge that they are attaching some muscle to. And I don't know what muscle it is. And it's like a key diagnostic characteristic of Brachypelma. They are so weird because they're the only thing I've seen that has this like enormous ridge that just comes up off the brain case.
And it's running laterally.
Yeah.
Weird.
Yeah. They're so strange. They do have some of the same like bite mark characteristics that Brachypelma does. So like you can see kind of one maybe right here. This texture right here is probably some bone bruising, but it's not nearly as extreme as in Brachypelma. Brachypelma, I genuinely don't understand how they survived, because they seem very intent on infecting and killing each other, whereas Brachypelma, at least, they seemed a little bit less destructive. Nobody has done like so there's been a couple of isotopic studies on like their teeth, but it's been on not these Oreodonts, and also it's been done on Oreodonts as a group. So part of the problem with not being able to identify Oreodonts is that sometimes they get reduced. So you get like 4 genera that are combined into, it's Oreodonts. Here's their isotopic range. But I suspect they probably were at least omnivorous. I'm sure that they do have like, deer-like teeth. Which
right.
But
so would those be in the realm of jerks then, or not quite to the level of a jerk?
So they're in this. They and the jerks are our sister taxa.
Right, perfect.
They're just not as big of jerks as the other ones are. Oh yeah, so this one's flipped over, and you can see there's some bone bruising and some like overgrowth here, and it looks like it's coming back here as well. That mostly looks dirty. Oh, poor Oreodonts never getting properly cleaned because there's 1,000 of them. Yeah. Oh yeah, but here you can see like healthy bone texture, right? Like this is what they should look like. Here's all that weird kind of rippling and like rugosity from various infections and healing. I'd say poor guys, but I'm pretty sure they're doing it to themselves, so it's really their own fault. Yeah, so conclusions. Oreodonts probably evolved trunks 2 or 3 times. They seem to be using them for different purposes, things like selective foraging and maybe something else. I'm not entirely sure what. They show that you can have trunks evolving from flexible lips and maybe from like cartilaginous snouts. And of course, the most important conclusion, Oreodonts are a 10 out of 10 and more people should study them because they're great. And that is it. I do have this little thing on here because I did open a paleontology clothing store, and that's the link. And so there you go. That's my one piece.
All right. So it's also episode 50 where we started advertising clothes.
That's right.
Fantastic. All right.
Unasked for sponsorships. Yeah.
Well, that is fascinating. I've learned a lot about Oreodonts today. I had no idea of the diversity.
Oh my gosh. Yeah.
I want to know so much more about them now. Yeah. That actually kind of is my first question is, how many people are studying Oreodonts? Do you have an Oreodont community that is kind of chasing down these really serious questions that impact almost every major museum in the world? Well, at least North America.
There's about 5 of us. And
with such a huge sample size. I mean, there's so many cool things you can do.
There's an enormous sample size. Like for Primaricaceus, the bitey jerks, I have like 70 skulls that I can look at that have like that are well preserved enough that they have their zygomatic arches. I have a nice cast just sitting right in front of me because, why not? Yeah, but I do want to point out that one of the conclusions also of the paper that is hopefully coming out this year is that even though they're very common, there's actually a couple of genera that are extremely uncommon. So if you have a Clistomicter or Hypsiops in your sample, please tell me, because there's like 4 of them in the world. So they're not actually that common, certain versions of them, but they're really abundant and there's a lot of different types and they're in every collection ever. So it's not like you're not going to be able to find them. And also I have thousands and thousands of photos and 3D models. So if you have a question, please let me know. I will give you all of the data I have because there's too much work. I can't possibly do it, even with the other people that I'm working with. Like there's so much to be done on Oreodonts.
If you're an Oreodont, where do you live? When do you live? Can you give us some context for, yeah, I mean, you see them, there's so many of them, but so many of the ones that I've seen are like White River material or something like that. Are there other places that are big bullseyes?
Yeah, and the geological range.
Yeah, so only North America. They never seem to really make it anywhere else. There are some that have been coming out of like Panama and Mexico, so they are getting pretty far south. There's some that have come out of Saskatchewan as well. They range from about 45-ish million years ago, so like Eocene, and then they go extinct by the Pliocene. So there's no Pliocene Oreodonts. Malcolm Thorpe thought that they were the most common animal in the North American Cenozoic. Probably Hypertragulus might be beating them out, but yeah, they are extremely common, especially in the Oligocene. So like White River Formation has a bunch. John Day has a bunch. John Day has like 5 different genera, 6 different genera, although currently they're written up as about 25 different genera. That is actually the curse of Oreodonts. There are so many skulls that you basically can see minor perturbations and you can be like, well, of course that's a different thing, because it looks slightly different. And they're kind of weirdly variable because they're related to camels, and camels just don't care. Camels do all sorts of weird things with their bone structure. They're terrible. But yeah, Oligocene anywhere, essentially in North America, you're going to find a fair amount of Oreodonts. Miocene as well, but they start to decline pretty quickly in the Miocene for reasons unknown. So someone can figure that out. That'd be great.
Yeah, it sounds like you wouldn't run out of projects with students to do.
No. No, you just run out of interest because they have to read all of the Schultz and Falkenbach manuscripts really fast. You know, if Schultz and Falkenbach wrote 5 200+ page each manuscripts about Oreodonts, just think about how much more research there could possibly be about Oreodonts.
Well, let's move over to David and see if he has any questions from the audience he wants to jump in with.
Sure thing. So as a reminder, now's the time. If you have questions, go ahead and put them in the Facebook comments, or if you can't do Facebook, like I said before, go to the Gray Fossil Site Twitter or Instagram account. Send us your questions there. Let's start. Here's a question from Jenny who says, what about the Oligocene Oreodonts that had big ear chambers for low frequency sounds? Could that be evidence of some Oreodonts using low frequency communication like modern elephants?
I actually don't know what you're talking about. Not that you're, there's just 1,000 papers on Oreodonts, and I read most of them and don't remember half of them. I do know that there are some studies on Myricoidodon in particular, because Myricoidodon is so beautifully preserved that they have ossified like larynxes. So there are actually some studies that have shown that they would have been extremely loud. So I'm not sure that they even needed to have kind of like that really low frequency sound production, because they were super, super loud. But it would not surprise me also to see that there was some low frequency stuff. Let's go back to the picture with all of the skulls flipped over. So this Statocaris has really, really limited auditory bulla. They're really, really small, and it's the same with Brachycrest. But things like Merycocharis and Promerycocharis have really big kind of bulbous auditory bulla. One of the problems that I found in Oreodont taxonomy is that people put a little bit too much emphasis on the auditory bulla. If you look at things like modern pigs and modern camels, they're actually a lot more variable in shape than you might expect. So like auditory bulla are really big in these taxa, but they're not super reliable, at least for identification, because they are really variable and kind of weird shaped. But most Oreodonts, with the exception of these kind of lineages, have really big auditory bulla. So yeah, I suspect they probably did have some pretty good sound production. They probably were forming herds and probably using some form of communication that way as well. But you should let me know what paper that was, because I need to read that one clearly, because I'm like, what? I don't remember reading that.
So it sounds like we don't know much about the way they were hearing sound, but they could produce very loud sound. Would this be more like a trumpet, like an elephant, or would this be more like a honk or something like that? Any thoughts on that?
I mean, I just have some personal thoughts, which I'm sure that these awkward creatures were making delightful geese honks, but like that's not a scientific opinion. From what I remember of that paper, it was just like, wow, they were probably really loud. Yeah. The obnoxious, I think, is probably a good.
The Canada geese of mammals, yeah.
Yes. Everywhere. They're everywhere, and they're only in North America. Yeah.
Well, here's another question, similarly about things that we probably don't know very much about. Gavin asks, are there any examples of soft tissues fossilized in Oreodonts?
I mean, that larynx, I think those are normally soft tissue, I think. I'm actually not super sure. There's endocasts, of course, but those aren't really soft tissue. I wouldn't be surprised if there were, but yeah, I don't know offhand of any examples of it. So I'm sure they were probably mildly fuzzy at least. Not feathery, not scaly, some variant of furry, but yeah, I don't actually know of any soft tissue. Oh, except for placentas. There's some like White River preserved things that have fetuses and placentas.
Cool.
I do have one here from Chris Jazz. For the non-swimming forms, are they all occupying the same types of habitats? How much sympatry do you think there was in the environments that they inhabited?
Ooh, so I mean, I don't think they can possibly have been inhabiting exactly the same habitat because you find them everywhere. So you do seem to find a lot of them in places like White River and John Day, which had similarly kind of like open, half forested sort of environments. But that might also just be a preservational bias because those two places tend to have decent preservation, and then they also have a lot of ash input. But yeah, they have to have some sort of differentiation because you have like in John Day alone, even though it's one ecosystem technically, you have 5 different genera. That's not even looking at species. And you have massive big pig ones all the way down to really tiny, tiny, tiny little ones. So there's no way that they were occupying the same ecological niche space. But I would say that the ecological niche space of Oreodonts, like everything about Oreodonts, is understudied.
And what kind of variation do you see in their feet in terms of their mobility within an aquatic habitat versus out in a more open area?
Yeah, so my studies mostly focus on skulls, just because skulls have been used for taxonomy, and a large portion of what I've had to do is taxonomy, just because I want to get to the cool parts. The early Oreodonts, the Agriaceae, they are clawed, so they all have claws instead of hooves. But everything after that has hooves. You do see some variation in things like Brachypelma has really big, solid kind of pig-like feet. There's some really cool specimens at the Carnegie Museum that died huddling together during a sandstorm. And if you look really carefully, they all have arthritis in their toes. So their toes are like really, really mangled and overgrown. And then you get things like Leptokinia, which even though it had hooves, they're really delicate. That actually has been one of the things that people have, and that I frankly kind of agree with, have used to say that it probably wasn't aquatic. If you looked at Leptokinia's, oh my gosh, so many animations. Keep going, keep going. There we go. Okay. So if you look at Leptokinia's feet, they're very delicate, right? They're not like kind of big hippo-like feet. So if they did, unlike like Brachypelma and Brachypelma and Mericurus both have much more robust toes. But I don't know enough about postcrania to even know if that's because they're just fatter and bigger, right? And they have bigger bodies versus a different lifestyle. There is an unpublished paper out there about Miniaceae maybe being a burrowing Oreodont. It's apparently found in quite a lot of burrows. They definitely had hooves. So if they were like actually digging burrows, that would be a very unique burrow digging experience. But that doesn't mean that they weren't necessarily living in burrows. You know, you could always move into someone else's home. Don't do that, please. Don't do that. That was not a suggestion for the public.
All right, we've got another question here. This is from Maggie, who asks, what might have caused the selection for such large canines?
So that's kind of an ancestral characteristic just to begin with. So if you look at this Agriacure up here, this face is largely reconstructed. They're not nearly as smooth and pretty, but they do have really large fangs. They're related to camels, Oreodonts are, and camels also have very large fangs. And I suspect it's more of a kind of defensive / sexual selection sort of thing. I've looked at Primaricoccurus canines, and while you can't seem to find like a nice bimodal curve, like where you have like big ones and small ones, they're highly variable, which suggests to me that you have males and females with slightly different sizes of canines. So I think it's more of a defensive / sexual selection. They do start to disappear in certain lineages. So like Leptocaenia, I mean, their whole face is small, but their canines are relatively small. Bathygenes, maybe that's why they were getting eaten by all the crocodiles. They have almost no canine left. If only they had bigger teeth, they could have bitten the crocodiles back. But yeah, with artiodactyls that have big canines, particularly since their teeth suggest that they did at least eat quite a lot of vegetation, even if maybe that wasn't everything they were eating. These teeth are probably more for defensive stuff than they are for carnivory.
All right, and then Ethan asks, does Oreodont evolution preserve anagenetic sequences of taxa?
So that has been suggested in a lot of Oreodont lineages, but it has been suggested without a lot of evidence behind it. I wouldn't be too surprised if there were some examples of anagenesis, but the thing about anagenesis is it's almost impossible to distinctly prove that it actually happened in the fossil record, because you're always missing pieces. So it could be anagenesis, or it could just be cladogenesis, and you're no longer seeing that other fork. I'm not a huge supporter of the anagenesis idea because I think that it kind of just ignores branching impacts in the fossil record. So maybe. What a horrible answer. Maybe.
Megan, it might be good for us just to mention what anagenesis actually means here.
Sure. So anagenesis versus cladogenesis. Cladogenesis is the idea that you have like new species kind of branching off from old species. Anagenesis is the idea that you have one species turning into another. So instead of a branch, like branching, you have like one single trunk.
Thank you. And Chris, I think you have a question or two.
Yeah, I mean the pathology, usually when we talk about taxonomy, especially when you have sample sizes like you do, pathology doesn't really come into play very much. So you must have a lot.
Oh
it sounds fascinating, but do you see this level of, I mean, I assume at some level it indicates, you know, some sort of dominant structure, some sort of social structure within herds or something like that. Do you see this level of damage on any modern animals that you can compare to?
No.
Okay. I mean, I've done a lot with bison, and I don't ever remember seeing, you know, a bison sample that has any kind of anywhere near the amount of pathology that you have.
It is, yeah, the amount of pathology on Oreodonts is kind of insane. And it is mostly limited to these two genera. This is a terrible photo, actually. Where is a better one? I mean, this one shows a little bit. This is like super kind of typical rugosity that you get from like bone bruising right here on the back of the zygomatic arch. I think probably part of it is we just have a ton of Oreodonts. So it is a little bit easier to find pathologic Oreodonts because they are super abundant. But I also wonder if maybe this particular lineage is just really prone to these bone infections. Man, where is the really, oh, here's a nasty one, isn't it? Ooh.
I mean, I wonder in looking at these if you're just not seeing a sexual dimorphism and the males are getting this sort of more robust, but also fighting and getting more infection from that.
So it also occurs in juveniles.
Okay. Maybe they're practicing.
I do, right? I do think actually. So for this particular study, because so much, so like here's some bone overgrowth here on the underside of the zygomatic arch. This is like a bone callus on this one where it's basically trying to knit back together. I do actually think with Primaricaceus, I do have that as part of my problem. I think I mostly have male Primaricaceus in my sample, because what I'm looking for specifically is I want Primaricaceus that have zygomatic arches. And if the females have smaller zygomatic arches, they're more likely to break, and therefore they're more likely to be excluded from my sample. But the fact that you do get these in juveniles, you get them in extremely old adults, you get them in kind of moderately aged adults. I suspect that this kind of biting behavior probably was mostly males, but it seems to have been at least very prevalent. There was a lot of combat or whatever in these groups. They were just really mean to each other. But like here's one that I think is probably a female. Oh, the zygomatic arch is reconstructed on this one, isn't it? Yeah, it is. Let's see if the other side was reconstructed. There we go. So this one is one that I think was female. And this is one of the ones, because it has really, really skinny zygomatic arches. It has a much more slender face. Of course, it's been called a different species because why wouldn't it have been? And this is one of the ones where it has this weird deformation of the zygomatic arch. In this one, that could very easily be post-mortem compression in the rock. Their zygomatic arches are not particularly well knit together. However, I have actually read papers on this happening in living humans. So if you get plastic surgery on your face to reduce your cheekbones and you chew too hard after that plastic surgery, your masseter muscle can pull your face apart. Oh, yeah. And so I don't know 100% with these if that's something that could potentially have happened. It's really hard to separate that from postmortem compression, but I see enough of them in this specific genus. I think I've seen like 3 or 4 at this point that have the zygomatic arches have been pulled specifically apart, that I kind of wonder if maybe this is a pathology and not postmortem compression. So painful.
Wow, episode 50 just keeps giving us amazing new answers and things to think about, because we've never heard anybody tell us how a face can get pulled apart.
Yeah.
Or how Oreodonts get plastic surgery. Yeah.
Right, yeah. How they relate. David, we're getting close to the end here. Do we have any other questions you want to throw in?
Yeah, we are just about right at the end. And actually, I had a question I'd like to ask. You spent a lot of time in this talk showing how the trunks come in a variety of different forms and for different functions, and the evidence for a trunk seems to range from very obvious to not particularly obvious at all. Mm-hmm. How likely do you think it is that there are a bunch of other extinct animals that had trunks and we just have no idea? Or are there any that have been suspected that no one's really pursued?
So, I mean, they're relatively consistent, but like the thing is, the difference between a trunk and a super hypermobile lip structure, that can be a little bit difficult to tell, right? Because if you have a trunk that doesn't have a lot of musculature, that's going to look very similar to a trunk or to just like a bunch of lip musculature, because you're moving your bone back essentially the same amount. I think that because that's so consistent, most of the things that have trunks, we probably can tell have trunks. However, that's in mammals.
Right.
Start to get into fish, and then of course my favorite paleo trolling, dinosaurs. Then things start to get a little bit fussier. So like Diplodocus, for example, has been theorized to have a trunk because it has its nasals have been moved all the way up to the top of its head. And it is my favorite thing to say that they did. Not necessarily because I believe that they did, but because I think that that is hilarious of a mental picture. And also because I know it makes some dinosaur paleontologists really mad. But there was a paper that was written like 5 years ago saying Diplodocus cannot possibly have a trunk because Diplodocus did not have big facial nerves. Well, you know what? Only elephants and tapirs have big nerves. So that means that if Diplodocus had a trunk, it just means it couldn't move it. It just
Mm.
would have had a big, floppy, useless organ on its face. And that is an even better mental picture. So yeah, I'm
So,
team trunk on a Diplodocus for sure.
so
Absolutely.
does that mean that a Diplodocus trunk would be more like Saiga? In which case, could we have had massive die-offs of hundreds of thousands of Diplodocus every now and then?
That's the more information for you right there.
Just like a
like
herd of whale falls.
Yeah. Oh,
I mean, just to go a little further, is there any way that could have caused the extinction of the dinosaurs?
I mean, from shame, possibly. Like an elephant seal face on a
All right, looking forward to the comments from the dinosaur paleontologists out there.
Currently, I don't think there are any dinosaur paleontologists in our comment section. Otherwise, I'm sure we would have heard from them already. But when they watch this after the fact, this video will be archived on Facebook and shared on YouTube, everybody, in case you want to watch it more or share it with your favorite Diplodocus enthusiast. Well, we are about at time here. There are a couple of other questions and comments that are in here that we haven't got a chance to get to. So Megan, if you want, feel free to take a look through those comments later. And if you see anything you want to respond to. But otherwise, a big thanks to everyone who has asked questions for this episode.
All right, well, thank you again to everybody for tuning in. Just to let those know who are our followers, and in the future we are going to switch over to an every other week, so we won't meet next week, but we'll meet in 2 weeks. And just to thank Megan again for this wonderful talk on Oreodonts. We had a blast.
Thank you guys for having me. Please study Oreodonts. Please.
All right, we'll see you later. Bye-bye.
Bye, everybody.